I hope you people are able to see my screen. So today we'll start with moving charges and magnetism, this chapter. So let us see. Okay, let me tell you a few words in the introduction of this topic, electromagnetism or moving charges and magnetism. So electricity and magnetism was known for a long time, almost some 2000 years. So they were known separately, and there was actually no knowledge about the interrelation between them. But since 1820, it was realized that electric field or electricity and magnetism, they are interrelated. Not only interrelated, they are intimately related. So it was actually first discovered, this interrelation was first discovered by a Danish physicist Ørsted. He was a physicist as well as chemist. During a demonstration, during a demonstration, he discovered the interrelation between magnetism and electricity. So let us see what was the demonstration. This is actually the part of demonstration I have shown here. This is part of demonstration. This is not the full experiment of the demonstration he had done. So what he was doing in the class, he was demonstrating that if actually what he was doing, he was passing current through a conducting wire. You can see that this is a conducting wire. So this is a battery, which is the source to give a potential difference between the across the wire, and the battery was connected through a switch. And look, this is suppose in the air. Somehow he has mounted the wire in the air, and you can see that the compass was kept, or compass needle was kept just below the wire, okay, or nearby anywhere in the nearby the wire. So when the switch was open, that means when the current was not flowing, that time there was no deflection in the compass needle, and compass needle was exactly showing the direction north and south. Suppose this, actually, as you know, compass needle always directed north and south. Okay, we'll see this. These are called actually magnetic north and magnetic south. This is north. If I just say this is north and this is south, okay, then I hope this will be okay. So this will be west, and right hand side this will be east. Okay, so this is the thing. Now the compass needle was showing this north and south, that direction, when current was not flowing in the circuit. But as soon as he closed the switch, current started flowing in this way. That means north to south. Current started flowing north to south direction. Then what he could notice that the compass which was kept below the wire, it is getting deflected. See, earlier north was here. North was exactly parallel to the wire. Okay, the wire is kept north to south direction, and current is actually flowing in that direction, north to south. And he noticed that the compass needle is deflected. Okay, deflected. Now this experiment was repeated by taking the compass needle just above also. So he could see that the compass needle is deflected in the opposite direction. In the opposite direction, okay. The north will be deflected in this way. If you keep the compass needle, so that's why I told it is partly shown, not the full experiment. So if you keep compass needle here, compass here, so what you will see, your north will be deflected this way, north, and this way will be south. Okay, this is north, and this way will be your south. South. Okay, so the deflection is exactly opposite, as you can see in the like below. The deflection will be exactly opposite on the above the wire. Now, if you change the direction of the current, see the battery polarity you have changed here. See the polarity has been changed. Here it is positive, this is negative. Now this is positive, this is negative. So current is flowing in this direction now, south to north. So once he had done that, he could see that the compass needle is deflected in the opposite way. Okay, opposite way. See, compass needle actually they have north and south pole. That means what? I hope you have some idea at least about magnetism from your previous classes, that this is south and this is north. So you can see, you can just think of a bar magnet. You have a south pole, north pole. So if you bring another bar magnet, or if you bring, yeah, if you bring another bar magnet, so south will actually repel each other, right? South will repel each other, like same poles will repel each other, and opposite pole will attract each other. So other than magnet, or other than any other magnet, see, if you bring any other material other than a magnet, what it will do? It will just attract, right? It will just attract. Okay, if it is not a magnet. So you can see what he concluded, that since the magnetic needle is getting deflected, then there must be a current produced, there must be a magnetic field produced around the wire. Okay, in the space around the wire. Okay, in the space around the wire. And see, this needle is actually getting deflected, or it is showing the direction. See, showing the direction of the north of the, see, actually I'll show you what is that. So it is actually deflected by the magnetic field created by this wire, okay, while passing the current. But if you don't pass the current through the wire, then there is no magnetic effect. So there is no deflection in the previous case when the switch was open. Now the deflection actually is reversed above. Okay, it is actually opposite above, because the direction of the magnetic field may be opposite. Okay, maybe opposite. So that was his conclusion. Okay, and that conclusion was rightly done by him, and that is true that nowadays we know that if you have a current carrying wire, it is producing a current around, sorry, magnetic field around it. Okay, around the current carrying wire. And I'll show you what is the direction. See, for the timing, I'll tell you here. Here there is something called thumb rule or grip rule, right hand thumb rule or grip rule. I'll show you here. If suppose this is the current carrying wire, and the direction of the current is upward, suppose. Okay. Now, if you just stretch your thumb finger, as you can see from here, if you stretch your thumb finger along the direction of the current in the current carrying wire, and with the other four fingers, if you try to grip the wire, in the way this figure is showing. Okay, so the tip of your four fingers actually give the direction of the magnetic field. Okay, magnetic field produced in this wire. Direction means what? So this side may be thought as north pole, and this side may be thought as south pole. because we know for a bar magnet, I think we'll show again, like your electric field lines. In case of bar magnet, we can draw magnetic field lines also. Magnetic field lines generally generated from north pole and enters into the south pole, and they form a closed loop. Actually, they form a closed loop. So you can see this side you can treat as north, and this side you can treat as south, because the magnetic field lines are just uh, suppose it is just going into, okay. So this is how you look. If I and see magnetic fields with, like, magnetic field created around the wire will form a closed concentric circles, okay, concentric circles like this. See, concentric circles like this. If you suppose, if you just reverse the current, then the direction of the magnetic field, see, now it is actually this way. Then you will look the, if you flow the current this way, then the direction of the magnetic field according to thumb rule, or this is group rule also sometimes called,
Clockwise.
because yes, it will be opposite. It will be actually in a clockwise direction. Yes, it will be clockwise direction. Okay. So you have to actually learn. You have to learn how to find out the direction of the magnetic field, because this is important. Many where you will see that we have to apply the grip rule or thumb rule. Okay. Now it is anti-clockwise. If the current is upward, if the current is downward, the magnetic field lines will be actually in the clockwise direction. Okay, and obviously they will also create. They will be in terms of concentric circles. Okay, circles, and where the wire is at the center. Okay, wire is at the center. Understand? Wire is at the center. Now see what he had seen. Another thing he had seen, that if you just keep the wire, and keep the compass needles around the wire. If you just pass around the wire, you will look that the compass needle is actually situated as if it is situated at in the direction of tangent. Okay, it is becoming a tangent to the arbitrary circle around the wire, having the wire at the center. So this is because the magnetic field lines are produced as a concentric circles. That is the reason. So that's why if you just take a cardboard, simple cardboard, okay, and pass a copper wire through that, making a small hole, and you just take filings of some irons or something, and just sprinkle it on the cardboard, and if you pass the current through this wire, you will see they will arrange themselves like in a concentric circles, okay, in a pattern having concentric circles like this. Okay, so from here he could conclude that the magnetic fields which are created by this wire actually forms a concentric circles, and you can see we'll actually derive these things further. So as you go further and further from the wire, the strength of the magnetic field will be reduced. But anyway, you can see that from the Oersted, the demonstrations of the Oersted, we can understand that a current carrying wire can create a magnetic field. Okay, and that magnetic field is actually deflecting your compass needle, and the direction of the deflection we can demonstrate very easily. You can see, I hope you will be able to tell me that if the current is in this direction, see, north to south direction, then how will be magnetic fields created? So they will be actually, if it is the horizontal on the plane of the paper, see, above it will be going like this, and down it will be actually coming this way, right, this way. So that's why So that's why this compass needle is deflected this way. But if you reverse the current, then look, then what will happen? So in above it will be this way, huh? Magnetic field line will be directed, and sorry, down, and above it will be like this. Okay, so this is why, that's why the north pole of the or the compass needle will be deflected in the opposite direction. So this is the way. Okay, to understand how this deflection was uh, observed by Oersted. Okay, and see, we'll be using some notations for magnetic field or current carrying wire. Suppose current carrying wire, this is suppose a cardboard or a page of a paper. So if the current current is actually coming out of the paper, then we will give a circle, like we'll make a circle and give a filled dot. Okay, so this will be actually the symbols for magnetic field or the current which is coming out of the page, out of page. Okay, and if the current is going into the page, then it is current or magnetic field is going into the page, it is denoted by a cross inside a circle. Okay, so this is into the page, and this is out of the page. Okay, so this is how you have to remember that this is actually universally correct. This is actually uh, universal rule. Wherever you go or whichever book you see, this is the rule that sometime crosses will not be given in a circle. Simply they will give you cross like this for magnetic field. In your book you will see sometimes, okay, like this. This means that magnetic field is into the page. Okay, and dot also, if sometimes dots are given like this for a magnetic field notation, so you have to think that magnetic field is coming out of the page. So with this small introduction, what we'll do, we'll start our discussion. So in this chapter, what we are going to learn, how a current carrying wire or a charge particle experience. Okay, so yeah, how a charge charge particle or current carrying wire can create a magnetic field around it, or how this wire or charges will be deflected by magnetic field, and many other things like, yeah, so yes, so these are the things we'll be learning. So see, magnetic field. So as I say, magnetic field, so we have seen in case of electric field in the first chapter, the electric field actually exert a force. Electric field exert a force on a charged particle. Similarly, actually magnetic field also will exert a force on charged particle. Okay, so that we'll learn here. But before that, let us just look back the electric field itself, and let us learn few concepts, like revise few concepts of electric field and how it is like exerting a force on a charged particle. So basically we'll learn what is source and what is fields, etc. Let us see. And how electric field is uh, exerting a force on a charged particle. Suppose I have a positive q charge over here. Okay, I'll just take a point charge, positive point charge over here. So what you know about field, that if I bring another charge around this, around the region, okay, around the region of this capital Q charge, so that charge will experience a force. Okay, and up to the region where this force will be experienced by the other charges, or the effect or influence will be experienced by the other charges due to this capital Q charge, that region is called field. Okay, that is called field. Okay, we know paddy field, we know like playground also is sometimes a field. Okay, so field means a region. Field means a region. This is actually crude way to say field means a region or a space, but field is something else you will learn in the 7th chapter. Field is actually can be expressed in terms of wave also. Okay, like in the electromagnetic wave we will see electric field has uh, its wave nature, magnetic field also has its wave nature. Magnetic field is denoted by B or H. Okay, so they have wave nature, and in combination they creates electromagnetic wave. Okay, so yes, so what happens, like this force exerted on this charge, or force experienced by this charge, which is actually F is equal to Q into E. This is actually a two-step process. What is two-step process? Suppose I have this charge. This is called actually source charge, which is creating a field around it, and this small charge is called test charge, because we are experimenting the presence of field created by capital Q with this small charge, small q charge. So that's why this is called test charge, and this is called source charge because it is creating the field. Okay, source charge. So look what happens. This charge creates a field around it. Okay, field around it, and that field interact with the charge which is kept here. Suppose small q. That field actually interact. Actually, they don't have. See, you can see this is very interesting thing, that how do these charges interact with each other. What is the medium of interaction between them? So that is the field. Okay, that is the field. So this charge will create a field around it. This will interact with this charge. In fact, this also will create a field around it. Okay, that's why this charge, in the definition of field, electric field, we say this is force by limit q tending to 0, force per unit charge. We say this. We take this field, this charge as a unity, or very very small. Okay, so that the influence of this field will not be affecting the position of this charge. Anyway, so you can understand that this is interaction between them is two-way process. First, it has to create a field. Okay, in fact, this also will create its own field around it, and these two fields will actually interact with each other. Okay, and what is the force? If you have a charge q, okay, and if you have an electric field, if you have uniform electric field, how do you denote a uniform electric field? Uniform electric field can be actually uh, represented by field lines and equidistant parallel field lines. Equidistant parallel lines. Okay, parallel lines like this. Okay, so yeah, so this is the thing. Now, if you have a charge here, small q charge, suppose here, it will experience a force, and that force depends on, actually the direction of the force depends on the nature of the charge. If this is a positive charge, it will be dragged by the electric field towards this, okay, or along the direction of the field itself. But if it is negative charge, suppose this is a negative charge, then that will be pushed this way, okay, in the opposite direction of the electric field. But now you have to understand one more point. This you have already learned in the static case. But suppose the charge is moving in this electric field, what is the force? Whether there will be force at all or not. See, field can even, see, field you have learned already, field can vary with space, and it can vary with time also. But now for the time being, we are taking that field is uniform. It is neither varying with space nor it is varying with time. It is a constant. So in that case, if the charge is moving or it is stationary, the force on the charge will be the same. Force on the uh, force on the charge will be the same. Okay, that is Q into E. Okay, if it is moving or it is stationary. Okay, suppose it is moving in the field with certain velocity, then also the force will be the same. Magnitude of the force will be the same. Okay, so this is one thing you have to know. Now I'll go to the magnetic force. What is a magnetic force? Magnetic force. And then we'll learn another thing here that is called Lorentz force. Before that, I'll just talk about magnetic force. So magnetic force, as you have seen, that electric field exert a force on a charged particle, whether it is stationary or moving. Similarly, magnetic field also will exert a force. Okay, suppose magnetic field is in this direction and charge is moving in this direction somewhere like this. Okay, Q, and this is B. So in this case with the velocity V, okay, in this case, in case of magnetic field, if the charge is stationary, charge is at rest, then there is no force, so force will be zero. If the charge is moving with a certain velocity, in a uniform electric magnetic field, then the charge will experience a force, and that force is called magnetic force, which can be expressed in this way: Q into V cross B. Okay, what is that? This is called magnetic force, and you can see from the this expression that the force will be there. Magnetic force will be there if the charged particle is moving in a magnetic field. If the velocity is zero, then force also will be magnetic force. This is called magnetic force. The force also will be zero if the velocity is zero. And so this is a cross product. You can see this is a vector. So this is a cross product, right? So how do you get the direction? You can get the magnitude, all right. Magnitude will be, so what will be the magnitude? So magnitude of the force will be Q, V, B and sine theta. If the angle between the direction of the motion of the charge and the magnetic field is theta, okay, if this is theta, then you get the magnitude of the magnetic force. But what is the direction? See, from the cross product we know the direction always will be in the direction perpendicular to the plane where the V and B are there. Okay, I'll just take this way. Suppose V is this and B is this. Then they are, suppose this is in the plane of the paper. So this is theta. So the direction of the force will be just perpendicular to this. Okay, this direction. This is the cross product, and here in the cross product, you know, like how to get the direction. I hope you people have already learned in the cross product in the 11th standard. But now I'll just, for your recap, I'll tell you how to get the direction of the product. See, if you just go for a cross product, there are two vectors A and B. So A cross B, suppose the quotient is C or result is C vector, then what is the direction of the C vector? How to find out the direction of the C vector? How do you find out? So this can be done using right hand thumb rule. This is called right hand thumb rule for cross product. This is right hand thumb rule, right hand thumb rule for cross product. Or sometimes screw rule also is there. If you so I'm not going to discuss that one because this is more helpful than the screw rule in this case also. So cross product. See what we do. Suppose I have to find out the direction of C. In this case, A vector is there. So I'm just calculating I cross K. Sorry, A cross B. A cross B, right? A cross B. So how to apply my this right hand thumb rule for cross product? So you have to, here I'll show you again. See the blue, sorry, green one is the vector A. So you have to, what you have to do, you have to stretch your 4 fingers. As you can see this shadow, 4 fingers. Okay, you have to stretch your 4 fingers along the direction of the first vector, which is A here, and then you have to curl your 4 fingers from the first vector towards your second vector, which is B here. Look this side. So this is B. So the arrow also has been shown. See, this way you have to curl. Then the thumb, actually the thumb which is showing you the direction of the vector C. Okay, thumb, in which direction thumb is getting stretched. Okay, this is deflected or stretched. See, if this is the case, in this case it will be upward. In my case, see, I was showing you B cross B here. So can you tell me which direction it will be? It will be towards you. If it is actually, if it is on the plane of the paper, then it will be upward direction. Okay, out of the page, right? Out of the page. So it will be actually out of the page. This will be your B cross B. Okay, if I just reverse it, then what will happen? Reverse in the sense, suppose I make this B and I make this as B.
Inside page, going into the page.
Going into the page. So then it will be going into the page. So what you have to do, you have to keep your 4 fingers towards B, and then curl towards this. Then your thumb will be actually pointing down like that. Okay, this is the way to apply your right hand thumb rule to find out the direction of the magnetic forces. Okay, magnetic forces. So we have got the expression for the magnetic force. Now suppose what I'll see. Now suppose there is a region where both electric and magnetic forces are there. Okay, fields are there. In this region, magnetic and electric fields are there. Okay, both are there in this region. And suppose my charge particle is entering into this region. So both E and B are there. Okay. So with a velocity, with certain velocity. Okay, with certain velocity. Then what is the force? What is the force? I'm not going to give the direction now, electric field and magnetic field. I'll just go give you in the next slide maybe. So what is the total force acting on this? Because both electric and magnetic fields are there. Or maybe I can tell you this is okay. Okay. So for the timing, let us not reveal what is the direction of this B and A. So what is the total force on this charge particle in this region? Because both electric and magnetic fields are there, and the charge particle is moving inside this region. So there will be 2 forces, electric force as well as magnetic force. So what is the electric force like on this charge? Okay, electric force will be
KQ.
Q into E. Okay, and what is the magnetic force? We have already learned the expression Q into V
B.
cross B. Okay, And see, these two forces can be added up, like you can just take the resultant, okay, and this resultant, suppose the vector sum of these two, so this resultant force is called actually the Lorentz force. Okay, what is this called? Lorentz force. So AFL, this is called Lorentz force, and this is obviously after the name of the scientist himself. So this is called Lorentz force, that is Q into, if I take Q common, so E plus V cross B. Okay, this is actually the Lorentz force. Okay, this is Lorentz force. Now we will see there are few properties. Already I have told some of them, but still we will discuss in the book. There are few properties of the Lorentz force or the magnetic force. If we look at the interaction with the magnetic field, we find the following features for magnetic force. So magnetic force, as we know, Q into V cross B, so it depends on, see, magnetic force depends on both the magnitude and the magnitude and the nature of the charge. It depends on the velocity, and it depends on the magnetic field where the charge particle is moving. Okay, so if the velocity is 0, then we have seen that the magnetic force on the charge particle will be 0. Okay, if, and this magnetic force, you can see if it is a proton or positive particle, then the direction in one direction, and the direction will be exactly opposite if the charge is negative. Now the magnetic force actually depends on, because it is a vector quantity, and you look, it is actually coming out of cross product of V and B. So the direction of V and B is most important. Okay, it is most important. So we know, yeah, V
Sir,
cross B means, yes.
sir, I have a doubt, sir.
What is your doubt?
Sir, in electric field, in finding force of an electrostatic force, we did not, sign is not mandatory of a charge.
No, it is mandatory. It is
In
mandatory.
this we have to put sign.
Where?
In
No.
charge.
No. It is not. Actually, it is actually mandatory for both the charges, both cases. Because see,
Okay.
force is a vector. You need to know the
Yes.
direction. I
Yes.
told you that electric field will be deflecting a charge particle towards its direction, and it will be deflecting a charge particle opposite. If it is negative, it will be deflected to the opposite direction of the electric field. Okay, that I had already told. It is there actually, both cases. It is for both cases. Yes. So it depends on the angle between V and B. If it is 0, because I know the cross product will give you sine theta. So if it is 0, then what will happen? Magnetic force will be 0. Okay, if the angle is 0. That means, what does that mean? Actually, that means if suppose there is a region where the magnetic field is along the x direction, and the particle also moving with the velocity in the x direction, okay, then what will be the force on this particle due to this magnetic field? That is 0. That is 0. Okay, if they see, if the magnetic field is this direction and velocity is in this direction, okay, velocity in this direction with the theta, so what will happen, like this is the V, you have to actually break the component. You have to break component of the velocity. You have to take perpendicular component in this direction and parallel component in this direction. Okay, parallel component in this direction. So like here, most important question is the trajectory or the path. Trajectory, a charged particle have in some, a charge particle has in some magnetic field B. Okay, so that is the most important question in this chapter. Okay, what will be the trajectory, in which direction it will be deflected, what will be the path of the charge particle. Okay, this kind of question will come again and again. We will show you here what is the thing. So you have to take both the components, perpendicular component as well as parallel component. So V cos theta this way and V sin theta in this way. So can you tell me which one will produce the magnetic force on the charge particle? Which component of the velocity? That is the perpendicular component of the velocity. Okay, and the other component, what it will do? It will not be affected by velocity, this magnetic field. So what it will do? This parallel component will drag the particle this way. Okay, in the x direction or the horizontal direction, and the other one, actually you have to find out the direction, in which direction it will be deflected due to the cross product. So V sin theta, so V is actually in this direction, so it will be in the downward. So look what will happen, the charge particle will be, the path of the charge particle will be something like this. Okay, something like this. In this case, like this, it will be a kind of a spiral. Okay, kind of a spiral. If you see for a certain time, if you don't see for the whole picture, at least you will see it will be deflected like this. Okay, but it will not make a circle. It will not make a circle. It will, because the parallel component is there, it will drag this way, and at the same time your perpendicular component, see the magnetic force on this part of this component of the force, what it will do, it will try to push this way in the downward, okay, or into the page, but this guy will push it in the forward direction. So that's why you will get a spiral kind of this. So the direction of the spiral will be like this. Okay, we'll see this is there. Okay, in the next section. So this is actually important. What will be the trajectory of a charged particle in a magnetic field? Sorry. So yeah, see here it is. So as I said that if the magnetic field is parallel or anti-parallel to the direction of the motion of the charged particle, it will not experience any force due to the magnetic field. But so when the magnetic force will be maximum, that is when the theta is 90. That means
Theta
when
is maximum.
Yes, 90. That means when the magnetic field and the motion, direction of the motion of the charged particle is perpendicular, that time it will be maximum. So you can read this portion carefully and see here. Here the direction is already shown. You can just get from the cross product. See, this is the velocity. See here the direction of the velocity of a charged particle point. Okay, so this may be a different one. So suppose your magnetic field. So this is, you just take a page which is perpendicular to the horizontal line. You just take a vertical page. Okay, page vertically, or you can keep your hand vertically like this, and see the magnetic field is actually from just passing through the page from your left to right maybe. And if the direction of the velocity is this way, okay, this way, then see the deflection of the charged particle, how it is. See here it is shown. You can see this is a negative particle, this is a positive particle. For a positive particle, it will be deflecting this way. Look, this way, and whereas your negative particle will be in the opposite direction. Okay, you can just see using your right hand thumb rule whether you get this. Right hand thumb rule, you have to get it. Okay, whether you are getting with the right hand thumb rule. Okay, so yeah, you try sometime this force direction, whether you are getting this direction of the force or not. I hope you will be able to get it if you demonstrate yourself as I showed. Okay, So I'll just go to the next portion. Okay, so here, look, okay, let me tell you this portion again. So what we have got from the magnetic force, actually sometime, in your exam, uh, see, I have got magnetic force like this, Q into, suppose theta is 90 degree, QVB. Okay, I'm writing QVB then. So sometimes they will ask you to find out the dimension of B. So always come from this force. It is easy to get dimension of magnetic field, okay, or magnetic flux density. This is called sometimes magnetic flux density also, okay. And from here also you will get the unit for B. Look, how do you get the unit for B? So unit for B will be, see, it is this is a Newton. If I just write B is equal to F by Q into V, so it will give you Newton per Coulomb into, this is actually meter and this is second here. So Newton second per Coulomb meter. Or you can do one thing, this Coulomb you can write as I into T, I into T. So T gets cancelled. So you can write Newton per ampere meter. Okay. So that is actually called Tesla, Newton per ampere meter. Look here, what I am doing, force. Okay, I'll just maybe clean it. So this is force Q into B. I have to find out the unit for B. So this is F by Q into V. So what I can do, I can just multiply T up and down. Sorry, that I'll not do. What I'll do, Q, I'll come from the definition of the Q. Okay, so Q, current, sorry, definition of the current. So Q means, see, I means Q by
per
T.
second.
Okay. Yes, I can write I into T. Then Q, I can write I into T. So that is what we'll write here in place of Q. So this is I into T. Okay, I into T. Now look, so I have unit this as Newton, this as ampere current, and this is second, and this is velocity is meter per second. So you will get second get cancelled, you will get ampere meter. So Newton per ampere meter, which is called as Tesla. This is after, so Tesla is denoted by T. Tesla, I think Tesla, yes, this is, sorry, Tesla. Okay, so this is after a scientist name. So this, actually, scientist Tesla also has very uh, significant contribution in this electromagnetism. You learn sometime in the history that he had, so Tesla, so actually he had contributed a lot. So that's why, and he had given this the unit of the magnetic field or magnetic flux density is named after his name, that is Tesla, and it is denoted by T. This is SI unit actually. Okay, SI unit of B is Tesla. And what is the CGS unit of B? Unit of B. So that is actually called Gauss. Okay, this is also after the name of scientist Gauss. Okay, so this Gauss and this Tesla, they have a relationship. So 10 to the power 4 Gauss. Okay, Gauss is denoted by capital G, is called 1 Tesla. Sometime in your a numerical problem, you may have to convert your Gauss to Tesla, Tesla to Gauss. So this you can remember. And if suppose, as I was telling, that if you have to find out the dimension of B, magnetic field or magnetic flux density, always come from this magnetic force. Okay. Okay. So this will be M L T to the power minus 2. This is I into T. Okay. And this is L T to the power minus 1. So this is how you can see this goes off. So you get L also will go off. So M T to the power minus 2 I to the power minus 1. So this will be your dimension for this B. Okay. All right. So yeah. Now what we'll do? We'll go to the next part. I have got another 10 minutes because I have started 6:10. We'll learn this one, magnetic force on a current carrying conductor. Magnetic force on a current carrying conductor. Okay, look, we have seen that we have learned already in the previous, like so far we have learned magnetic force on a charged particle. So what we are going to learn now, magnetic force on a current carrying conductor or wire, current carrying wire. Look, you might be surprised that how can a wire, if I keep a wire like this in a magnetic field, suppose my magnetic fields are like this, or perpendicular, maybe anything I can take. This is a conducting wire. Okay, this is conducting wire. So this wire will be experiencing a force due to this magnetic field. How is it possible? Why not it is possible? It is possible because see, we know, we have already learned the charged particles experience a force in a magnetic field. And what this current means, current carrying wire means, the current carrying wire or conductor, they have plenty of charged particle inside. And what type of charged particles they have? They have basically free electrons, right? Conductors, they have electrons of the charged particles, and flow of charge is actually current, right? Flow of charge is actually current. Flow of charge or time rate of flow of charge, I can say time rate of flow of charges actually is called current, electric current. Okay, this is called electric current. Okay, so that means conductor also consisting of charge carriers. So if you keep a conductor, current carrying conductor, obviously when the conductor, through the conductor current is flowing, that time it will experience a force, otherwise not. If the conductor is there, it may experience, but if the current is flowing through that, then the strength of the force will be more. Okay, understand? In fact, what we are going to discuss, the magnetic force on the current carrying conductor when the current is flowing through this. Okay, current is flowing through that. So that is the time we are. So suppose I have a current carrying conductor, okay, which is placed in a uniform magnetic field B, and I suppose the length of the wire is L, and it has a cross section area A. Okay, and suppose I am just looking for a delta time interval. That means current, I am just, suppose switch is on, current is flowing. After delta t time, okay, I'm just like during delta t time interval, I'm seeing the force on this charge particle. Okay, so look, we have already learned inside a conductor, electrons move with an average velocity which is called drift velocity. Drift velocity, and that is denoted by Vd. Okay, that is denoted by V suffix d. That means when there is current flowing through the conducting wire, the charged particles are moving. Electrons, in fact, electrons are moving. All of them are moving with a uniform velocity. Average means uniform velocity, and all of them has the same velocity Vd. Average and uniform. This is uniform velocity. Okay, and that happens when there is electric field across. Electric field is applied, or there is a potential difference across this across the end of the wire. Okay, or across the wire. Okay, so now look what I can do. I can see. I take another assumption that there is a charge density in this conductor n, small n. That means what? Charge density means what? Total number of charge per unit volume. Okay, and this has uniform cross section. Okay, uniform cross section. These two assumptions are made. So what happens? I can get the total number. See, I know the magnetic force is actually, see, if I want to know the magnetic force on this conductor, then I need to know what I need to know. Look, I have expression for magnetic force is Q B. Okay, so B cross B. So this I need to know. What is the velocity of the charge particle? What is the magnetic field? Obviously, magnetic field is given. What is the number of charges? So I need to know what is the number of charges in this conductor. So how many numbers of charges are there? You have to find out here. So suppose in dt time, how many charges gone? So see, if the length is L and the area of cross section is A, then this is the volume. So then how many charges are there? Total charges. I know the charge per unit volume is actually small n. So total charge, this Q I can write as N into L into A. I hope all of you will be agreeing with me. And what is the velocity? All of them has velocity Vd, drift velocity, right? Drift velocity. So far, no problem, right? Okay. I'm just taking the suppose I am taking, this is vector. Suppose I take the magnitude of the force now. So I get N L A V D B sine theta. We'll just take the this as 90 degree or maybe anything. Let us not bother about the direction first. Now let us first bother this thing. So N L A. See, look, this is actually, I'm sorry, this is the total number of charge. I have to multiply the amount of charge for each electron. If I just know the charge for each electron is Z, so total number of charge will be actually, total amount of charge will be NLA into this. Okay, I just had done some mistake here. So total charge is, this is the total number of charge, and if you multiply the charge for each electron, then this is this one. Now look, we have learned already. If I take this N E V D into so NE VD into A, this term will give you the current. Okay, we know current density is actually N E into VD. This we have learned in the second chapter. Okay, if you remember. Yeah, second chapter. Yes, second or third. In the third chapter, I guess. Third chapter we have learned this. Current density is N. That is the density of charge. E is the charge for each electron, and VD means drift velocity of each electron. So this will be current density, that means current per unit area. Current per unit area, that is J, denoted by J. And if you multiply A, then you get the current. Okay. So this term I'll write now you have remaining L, B, and sine theta, right? These are remaining. Look, this if I write I, so what I get? I, L, B, sine theta. So what I got? So the force, magnetic force on a current carrying wire is I, L, B, sine theta. This is the magnitude. If I want to write in terms of vector, I can write I, L cross B. Okay, I, L cross B. So this is the magnetic force on a current carrying conductor. Okay, so no problem from this line to this line, right? Because this is sine theta, I can write in terms of cross product. So I have written, see, I into L. See, how do you take the direction of L? Actually, you have to take the direction of L in the direction of current always. If you have a conductor carrying a current, its length is this. Length, actually length is L. Length is L. So it doesn't give you direction. So how do you take the direction of the current? A direction of the L. So how come you get the direction of the L? So you have to take the direction. If it is going from west to east, you have to take the direction of L also as west to east. Okay. If it is along the, if the current is flowing in the x direction, then this will be along the x direction. Okay. If current is flowing in the minus x direction, then L, direction of L will be minus x. Okay, this is how you have to take the direction of the length of the wire. Okay, this is length of the wire. This is, length is not a vector, length is scalar quantity, but it can be a vector quantity as a whole if you take the direction of the length of the wire in the direction of the current. Okay, so this is I, L cross B. Suppose you have a conductor of arbitrary shape. Okay, arbitrary shape like this. So it will be very random. I'll just take like this. Okay, arbitrary shape. Then how do you apply that magnetic force? It is said that you can divide this into small part. Suppose some dl. Okay, dl, and see, as electric force or electric field and everything follow principle of superposition. In this case also you can apply principle of superposition to get the total amount of force. If you just break into small part and find out the actually total current will be flowing the same, I dl cross B, you have to find out the force. Okay, suppose this is F1, F2 for the other one, like that. If you find out all of them and then take the summation over them, I dl I, okay, cross B, I goes from 1 to n, suppose n parts you have made. So this will be your total force on the magnetic force on the current carrying conductor. Okay, if the wire is not uniform, okay, having some arbitrary, suppose it can be a circular also or some curvature like this. Okay, so you can just break small part. Okay, and then calculate the total force on this. Okay, so this is how you have to learn magnetic force on current carrying conductor. So I think I'll stop it here. I have taken some 4 minutes extra. So thank you all of you for your questions. So I don't have time for you to like I don't question back whether you have learned or not. But what I'll do, I'll just take a special class for discussion various type of problems or questions. So that time I'll ask all of you people, or if you have any doubt anytime, you can stop me and ask me your doubts. Okay, so for today this is all. I hope you people have understood. You can just go back and read. If you have still some doubt, you can ask me in the next class. Okay, so we have yeah, so I think we'll stop it here today.